Hi roboticists, welcome in this new video where we're gonna learn how to orientate the end effector of our robot with respect of the frame word by using transform. And thanks to that, you will learn how to use the quaternions in a very practical ways instead of making a lot of mathematical calculations. So, before to start, make sure to subscribe to the channel if you like this kind of topic and robotics video, and turn on the notification bell to do not miss the next topic. And now let's get started. So, if you remember from the last video, we have code an API C++ code using MoveIt that makes our end effector, or better TCP, move in a certain position in translation and orientation using quaternions. Well, quaternions is a way to interpret the orientation of a certain link with respect of another frame. And last time we have set up just a simple quaternions with the real part 1 and the other imaginary components of the vector as 0. And I can understand you if you struggle in imagine a quaternions, because you are used to orientate your TCP with respect of the yaw, pitch and roll. So the scope of this video is to understand how to orientate your TCP without making a mathematical calculation, with a visual approach and, in my opinion, very intuitive one. Quaternions are a mathematical tool for identifying the orientation of a frame with respect of another. I know that it's difficult to imagine the quaternions because you have 4 parameters, 1 real and 3 imaginary, and I guess that you are used to thinking orientation with respect of roll, pitch and yaw, like what you are doing by moving the end effector in Rviz by using the MoveIt plugin. I don't want to go into the detail of the math of quaternions. There's a lot of information in internet and also a good video available on YouTube to visualize it. And I'm gonna provide the link in the description down below, but you need to know that if you have a frame that is rotating with respect of another, you need to solve a matrix, or better the orientation matrix, that has 9 parameters contained in the rotation matrix. Quaternions, on the other hand, have 4 parameters, with the drawback that it's difficult to visualize a rotation made with quaternions. So what we need to do is to find a way to put the quaternions values into our C++ code that represents how the end effector, in our case the link that we have named in our URDF file gripper connector, is orientated with respect of the frame word. But why it has to be related to the frame word? Well, because from the translation we can see that the position of the end effector is x1, y1 and z1 with respect of the center of our environment. So meaning that the quaternions orientation is with the respect of the word frame. To figure this out, we need to introduce the concept of transform. So what a transform in ROS is? Well, transform is a way to track over the time the position and orientation of a frame with respect of another frame. If two frames are fixed with respect to each other, we have a static transform. If one frame is moving, then we have a dynamic transform, which will be our case in our six-axis robot application. So, as a recap, transforms tracks the position and orientation between two frames over the time. And for our pick and place application, most often you will be faced a situation where you need to track the position and orientation of your end effector of the robot with respect of a certain frame, and in this case and most often is the center of the robot, the reward or the base link, for example.
Okay, there's a way to visualize the transform, and the most practical one and the visualization method is to add something to display and looking for transform that is going to be here, and here you can see the link in yellow, all the transform that are available in our robots. So let's expand this. And for example, let's click frames, expand frames, and deactivate everything that's regarding the camera. And here you can see here that each link, or better the consecutive link of our robot is correlated via a yellow link that is going to be transformed. So the word is linked, is connected via transform with baseline to link 1, the origin of link 1 to link 2, the origin to link 2 to link 3, and so on and so forth. So what we need to do, as you can see, the transform are related to a link that is close to each other. So you should not have a link 2 related via transformer to link 4, but instead it will be link 2, link 3, and link 4. So what you need to do if you want to have a transform between the end effector, that in this case will be our gripper connector, which is gonna be this rectangular frame here at the edge of the robot, related to the base link or the word. What you need to do is to broadcast a transform between the parent link, that is going to be word in our case, and gripper connector. So for make things clear, let's deactivate all the link and just connect only what we need. So here you have the word frame and the gripper frame. Okay, so what we are going to do is to create a broadcaster that is able to create, let's say, a transformer between word and gripper, and we will track the position and the orientation of this frame gripper connector related to this other frame word over the time. So, for example, what we're gonna build is a node that when we move the TCP in a position, then we click plan execute, and then there will be a node. We will echo the transform topic, and we are gonna see how this transform is over the time. So when the gripper connector will reach the target position. Then there will be displayed the position and the translation in quaternions, and we are gonna substitute in our C++ code here. So now we can start to code, and to do that we just need to create a new package that we can call it Cobot_TF, that stands for transform. And what we need to do is to put the dependencies that will be very useful. So there's gonna be ROS CPP, then standard messages, then tf2_ROS, then geometry message, and tf2, and tf2_messages. Then after that click and type enter and build the package by typing catkin make as always. So go into the source folder and create a new file, and we are gonna call it a tpc broadcaster.cpp. And then first you will need to include the package that you're gonna use, that is gonna be tf2 linear quaternions, then tf2 messages, and transform, and transform stamp belonging to a geometry messages package. So why this? Well, we are gonna figure it out in a moment, and we are gonna see that the transform topic, which is the topic that we need to focus on, is a topic that contains a message of type geometry message form stamped. And in order to check that, well, we can launch Rviz, where there's the configuration package of MoveIt. Type ROS topic, then we're focused on transform message, so we get the information of this topic transform, and we can see that is of type transform 2 messages transform message. And if we want to go deeply in that message, we can grasp the information by typing ROS message info tf2 messages and the tf message. And finally we can see that this message is of type geometry message transform stamped, and these are all the information that this message provides, like the header, the parent link, transform, and translation, and orientation in Quaternions. So after this introduction we can build our main section, and it's very simple one. We just need to create a subscriber that is subscribing to the topic transform, and is going to handle this message by the callback function that we have called pause callback. And this callback function gets as an input a message of type a geometry message transform stamped, and we can name it MSG.
So now we need to go the callback function, and we need to create a broadcaster which is of type transform to ROS, transform broadcaster. And then we need to create a transform stamped object that we can call it a transform stamped. And then we need to, let's say, construct our object transform stamped with the respect of all the properties that this object has, as we can see from the ROS message info. And so we need to create a header stamped, and then the header that in our case will be header frame ID, that will be our reference point, that is gonna be word. Then after that we need to have the child ID frame, that is gonna be the gripper connector. Then we can set the translation, and finally the orientation. So we just need to type transform dot translation, then X, and repeat it for Y and Z, as illustrated in the info of this message. Then we need to create a Quaternions object, then set the roll pitch yaw to 0, and then make a transformation between the roll pitch yaw to Quaternions orientation by using the Quaternions embedded in the function. So we have created our object transform stamped, and then we just need to broadcast this transformation by typing BR, that is gonna be our broadcaster object, and then send transform and the object that we have just constructed. Then before to test it and build the package, I remember you that you need to ask CMake to create an executable file from the CPP file that we have just created. So after having built your package, what we can do is to test this broadcasted out. And how to do that? Well, just open Rviz, and then try to visualize the transformer that we are interested in. So a transformer that links, let's say, the word frame with respect of gripper connector. And then what we can do is to run the custom pathway that we have set up in the last video, and in the meantime check what will be the position and orientation of our TCP with respect of the word, and the result should be the same that we have set up in the C++ code. So run this code, and meanwhile we are checking, we are echo, let's say, the broadcaster from the word to the TCP, and you can see in live that the translation and rotation in quaternions, so that is the dimension that we are interested in, is changing simultaneously. And if everything is good, the translation will be 1 1 1 with x y z, and the quaternions will have all the imaginary data to 0 and the real part to 1. And as you can see, it works. So the TCP is in the custom target position that we have set up in our C++ file. For remember the test custom CPP file. So the gripper connector is in 1 1 1 and rotation quaternions that we have set up. So if we come back, then we are gonna have the TCP in the 0 position that we have set up in the MoveIt configuration wizard. And here we go. When the transform is not changing over the time, meaning that the robot has reached our target position. Then, for example, we are gonna go into the detail of this video, and we are gonna change the orientation and the position of our TCP, and then we will see what will be the orientation in quaternions. So instead of making mathematical tools, we just need to set our TCP in the target position that we want, for example a peak position, and then check with echoing, let's say, the broadcast that we have created, what is the position and orientation of the TCP. So to make this happen, you just need to click in the MoveIt plugin Rviz execute pathway, and then you will see that the reference frame is word and gripper connector, and the transform is changing over the time. So here we go. You can see that the translation and rotation doesn't change anymore, meaning that the robot has reached our target position, and this is the position in translation XYZ. And you can see that if we consider that the word framing is in 0 0 0, well, the translation coordinates are good, and these are the quaternions position. So the first three will be the imaginary part, X, Y, Z, and the last one will be the W. So what you can do now, I let you do by yourself, is to check this by modifying the orientation and position of our target position in the C++ file that we have created in the last video. So very easy. I suggest you to copy and paste. Remember to delete afterwards. Then build the package again and run the demo.launch file from MoveIt and run the node cobot, the node test custom cobot.cpp executable file, and you will see that the TCP will reach the target position that we have set in this file, and we have figured out the orientation in quaternions by echoing, let's say, the broadcaster that we have created. So that's all for today. I hope that you enjoyed this video. If you like this video, make sure to subscribe to the channel and hit the notification bell to do not miss the next topic. It will help me to improve the quality of the message and create more topic. For example, the new one that is going to come, which will be regarded to the object avoidance, which will be very interesting. So thank you for your attention and keep learning robotics with ROS.